Here we're asked to find all the points of inflection for the curve y equals 2/3 x to the power of 3 minus 6x squared plus 16x plus 1. So how do we attack this? Point of inflection's possible. POIs occur when d2y dx2 equals 0. Now I say the word possible because every time d2y dx2 is equal to 0, we don't necessarily have points of inflection. Just to give you a little example, if you had y equals x to the power of 4, now the first derivative, so y dash would be 4x cubed, and y double dash is equal to 12x squared. Now to see what's happening with concavity on either side, so firstly, when we have the second derivative equals 0, so y double dash equals 0 when x equals 0. That's pretty obvious by looking at that. So if this is equal to 0, the only value of x that'll make that equal to 0 is x equals 0. So you have a possible POI when x equals 0. And how do you find out whether you actually get a point of inflection? Is you put values in on either side of x equals 0. So x equals -1, y double dash is equal to 12, and x equals +1, y double dash is also equal to 12. Now that tells us that the concavity has not changed, and we have points of inflection occurring when the concavity does change. So that's just to highlight that you don't always get points of inflection when the second derivative is equal to 0. Y equals to x to the fourth looks at a very steep y equals x squared curve. So certainly you're not having a point of inflection occurring there, you actually get a minimum occurring there. So what we need to do here is firstly find the second derivative. So just like finding turning points, the first step was to find dy dx. POIs, our first step is to find d2y dx2. So dy dx first, let's start first things first. The derivative of that will be 2x squared minus 12x plus 16, and d2y dx2 will be the derivative of this, and we get 4x minus 12. Okay, so our next step, just like we did with turning points, is to find x values. d2y dx2 equals 0, and we keep in mind that we don't necessarily have a point of inflection when this happens. So we've got 0 equals 4x minus 12. Take the -12 to the other side and you get 12 equals 4x. Divide both sides by 4 and you get 3 equals x. So at x equals 3 we have a possible point of inflection. What was the third step with turning points? So going back to our template idea, the third step was to find corresponding y values. And if there are more than one x value when you have the second derivative equals 0, well, you've got to find more than one y value. So when x equals 3, y is equal to 2/3 3 cubed minus 6 3 squared plus 16 times 3 plus 1, and that should work out to be 13. So possible POI at 3,13. Okay, so we've got the first three steps, and the fourth step is to determine if POI exists. How do we do that? We substitute x values into the second derivative on either side of 3 and see what happens to the concavity. So a bit of a fan of tables. So we've got x d2y dx2. So we know when x is equal to 3, d2y dx2 is equal to 0. Let's just put in, say, a value less than 3 that's easy to put into the second derivative, so 0, and another value that's simple to put in, so we've gone 3 down, so let's just go 3 up and we'll go up to 6. So if we put 0 into dy dx, now, sorry, d2y dx2, now d2y dx2, from what we've done up above, d2y dx2 is 4x minus 12. So all we've got to do is put 0 into that, and we get 0 minus 12, so that'll be negative 12. When we put 6, 4 6s are 24 minus 12, so that's equal to 12. Now, the second derivative tells us about concavity, and because the concavity is negative, so this is, we'll talk about concavity here. And when the second derivative is negative, it is concave down. And when the second derivative is a positive, so positive 12, any positive number here, it's the second derivative, we are concave up. And obviously we don't have any concavity at 3. So the sign of the second derivative has changed on either side of x equals 3, so that tells us, yes, we do have a POI. And this also helps us to confirm that we've gone from concave down to concave up. Now, if you are asked to sketch that, we're not asked to do it in this case, but just to show you what's going on. So at x equals 3, we have a point of inflection, and in fact it actually goes a little bit like so. It has gone from concave, so everywhere here we are concave down, and from here out it is concave up. And actually that will extend out indefinitely because the graph continues down there. Okay, so that's sort of an example of how to do it. It's very similar to finding the nature of turning points and all that sort of stuff, but in this case, instead of just finding dy dx, we find the second derivative to determine POIs. Possible POIs happen when the second derivative is equal to 0, and then we look at the corresponding y values, and then we simply see what's happening on either side, either x values, pick values that are fairly close. In this case, because we've only got one possible POI, I went a little bit further away. I went 3 units either side. You could have gone 5 units, you could have gone 1 unit, you could have gone 2 and 4. It really would not matter in this case. And if the sign of the second derivative changes, that means the concavity changes, and that is a test for a POI. So we finish by just doing a quick little sketch.